Welcome everyone to the video mentioned in the 26 billion kilometer scavenger hunt. If you look closely at this picture, you'll notice it says the solar system is big, but atoms are bigger. Now is the time to reveal what that means. Let's first meet the characters of the story, starting with the solar system. The sun, of course at the center, isn't to scale, but the orbits of the planets are scaled to each other. First we see the orbits of the four inner planets, and then, after the mostly empty asteroid belt, those of the gas giants. For simplicity, Neptune's orbit, with a radius of 4.5 billion kilometers, will represent the solar system from here on out. Then we have the atom. In order to keep things simple like the solar system, I have chosen ground state hydrogen. This depiction with the proton in the center and electron orbiting as close as possible is known as the Bohr model, or more fittingly, the planetary model. It's no quantum model, but it sure is easier to work with. In the case of the ground state hydrogen atom, the distance to the electron is known as the Bohr radius, another reason to use this model, which is a minuscule 5.29 times 10 to the negative 14th kilometers. If you're thinking that the video should end now, since that's way smaller than 4.5 billion kilometers, you've forgotten one thing: scale. This is where the usefulness of the planetary model comes in, since both it and the solar system have something in the center. Right now, those objects are of different sizes, and to fix that, we will make the proton as large as the sun. What we need to know is how much to scale it by. In 2015, the International Astronomical Union passed Resolution B3, setting the nominal radius of the sun, when used as a conversion factor, as exactly 695,700 kilometers. Now, there is debate about the radius of the proton, but recent research suggests it is near 0.84 times 10 to the negative 18th kilometers. Comparing the two results in a scaling factor of 8.28 times 10 to the 23rd. If the proton radius is scaled by that factor, then so is the Bohr radius. So now let's put the sun-sized proton at the center of the solar system and go find the electron. We first encounter Mercury 60 million kilometers away, but not the electron. Venus is 105 million kilometers away, but the electron's not. 150 million kilometers on, we don't find the electron anywhere near our home. The last of the inner planets is 225 million kilometers away, and we don't find the electron here either. The asteroid belt extends to about 495 million kilometers, and we find nothing. The first of the gas giants, Jupiter, pops up around 780 million kilometers, and there is no electron. Saturn is next, just over 1.4 billion kilometers away, but the electron's nowhere to be found. Uranus, happily rolling along in its orbit, is also not close to the electron, even though we are almost 3 billion kilometers away. The last of the gas giants and extent of our solar system is 4.5 billion kilometers away, and there is still no electron. Pluto, the last natural object included on our journey, is close to 6 billion kilometers away. New Horizons, which took that previous picture, is over 8 billion kilometers away. Pioneer 11 has traveled 16.5 billion kilometers. Voyager 2 and Pioneer 10 have traveled nearly 19.7 billion kilometers, but neither are close to the electron. Voyager 1 at 23.5 billion kilometers away and in interstellar space has yet to pass the electron. Light, which travels 25.9 billion kilometers in a day, needs to travel a bit more to get to the electron. Moving to 30 billion kilometers, nothing. And even 40 billion kilometers isn't enough. Finally, at a distance of 43.8 billion kilometers from the sun-sized proton, we locate the orbit of the electron. This is such a vast distance we could use a bit of context, and it helps to actually get rid of the electron for a moment. Earlier we defined Neptune as the end of the solar system, and at that size nearly 5 entire solar systems can fit within the distance between the sun-sized proton and electron. It would take light roughly 40 hours to travel that far. But those with some knowledge of the atom know that the electron location is far from fixed. In fact, the electron can occupy any number of orbits, or more properly, orbitals. What this green line represents is the first orbital, known as 1s. The electron can move orbits if it is excited, and if it moved to the next closest orbital, known as 2s, that would represent the smallest excited hydrogen atom possible. How far away is it now? Over 260 billion kilometers, which is so vast that 29 entire solar systems can fit within that distance. Now you might think I'm not being fair to the solar system, and you may have a point. Let's get rid of hydrogen and switch to helium, the second most abundant element in the universe. It has 2 protons and 2 neutrons in the nucleus, which makes it more massive than hydrogen. There are also 2 electrons to balance out those protons. Now I will apply the scaling factor, and let's chase after that electron to the right. And here we find it a mere 25 billion kilometers away. If you can make out the tiny gray dot on the left, what you are seeing is the helium nucleus. The helium atom is more massive than hydrogen, but it has a smaller radius. Even so, you can still fit over 2.5 solar systems within that distance. I could not have given the solar system a better chance to redeem itself. Surely now you are convinced that the solar system is big, but atoms are bigger. However, before I go, we must take one last look at the proton. We scaled up the radius of the proton, but that's not the only property that would change. The mass of the non-sun-sized proton is minuscule, but it has an astounding density. So if there was a proton as large as the sun, its density would remain the same, but it would have a mass of 9.45 times 10 to the 44 kilograms. This mass is huge, and talking in kilograms isn't going to cut it anymore. We need to go supermassive. To date, only 2 black holes have ever been imaged. Sagittarius A star at the center of our own Milky Way has a mass equivalent to 4.2 million suns. The other one at the center of M87 is in the neighborhood of 6.5 billion. The sun-sized proton is so massive, it is equivalent to 475 trillion suns. Now, according to what I could find, the theoretical maximum mass of a black hole is estimated around 50 billion suns, which means the sun-sized proton is nearly 9,500 times more massive than the theoretical limit. So what exactly would happen if this mass was present in a volume the size of the sun and physics took over? I have no idea, but that seems like a question perfect for Kurzgesagt. So perhaps I will email them and see if their brilliant creators can find some answers. If you never heard of that channel until just now, check them out and you can thank me later. But before you go, let me thank you very much for watching. If you have any suggestions for other ridiculous comparisons I should make, leave them in the comments.